I would like to invite Pablo Semio Castro, if he's on the call, to do a quick intro to this session, if he's available. Pablo, are you with us?
Yep. Hi, everyone. Sorry, there was a bit of confusion as to GatherTown or Zoom. I was in the GatherTown, but I'm glad we're not too late joining. So hi, everyone. My name is Pablo. I'm a researcher in Google Brain in the Montreal office. And I've been involved with LatinX and AI efforts for quite a while, almost since the beginning. And so I thought it'd be a good idea to have this type of mentoring research pitch session. I've been supervising a few students for the last little while, and those arose as a consequence of the LatinX and AI events. So one of them in particular, Johan, I met him at one of the earlier LatinX and AI events, and we kept on chatting, and he'll be joining Université de Montréal as a master's student, and I'll be one of his supervisors. So that's all just to say that the importance of these types of events, that they help foster these collaborations and allow you to meet these people with which you might end up writing research papers with. For some of us in Google Brain, it's unless we're actively looking for these types of collaborations, it's sometimes hard to find how to start these things or to meet the people that you might get involved with, especially if you're not explicitly involved with one of these efforts. So I've invited a few people from Google Brain to present a few research pitches, as well as some people from our community here to present research pitches. And the idea is really to, talk about what interests you, what you'd like to investigate, and see if there's something that resonates with you. And if so, hopefully, as a follow-up of this event, you can start some of these collaborations. So I think there's a bit of a communication issue with some of the Google Brain folks that are in Mountain View. It's kind of early for them, I guess, for many of you. So we're going to shift the schedule a little bit. Since I'm already speaking, maybe I'll start giving my pitch, and then we can continue with the presenters that are currently available. So as a reminder, the plan is to have about 3 minutes for each presenter. So I will be keeping time. If you're presenting, if you want to monitor the chat, I'll be putting in sort of reminders. You have 1 minute left, or you have 30 seconds left. So I'm going to start one for myself, and first let me share my screen. Okay. So I will start now. So again, my name is Pablo. I'm a researcher in Google Brain, and my main research area is reinforcement learning, and in particular, deep reinforcement learning. So some of you may or may not be familiar with reinforcement learning, but if we look at deep learning at a high level, what we're really doing is we have a big data source here on the left, and we feed it through some deep network, and then we get some desired outcome, whether it's classification or generation or recognition or something like that. In supervised and unsupervised or semi-supervised learning, typically this data source is fixed in that it doesn't change. But in reinforcement learning, especially in what we call online reinforcement learning, this isn't the case. We don't have a data set. Instead, we have an environment that our agent that we're trying to train interacts with. And so as the agent interacts with the environment, it gathers new data on which it trains. We also in reinforcement learning don't typically have a desired outcome in the sense of labels of whether we're classifying correctly, or if we're recognizing things correctly, or if we're generating the right type of image. Instead, what we have is something a bit more abstract, where we're trying to maximize the sum of rewards, but we don't know where these rewards come. So this makes it kind of challenging as well. And so what we end up doing is using a method called temporal difference, where we're leveraging our previous estimates to build up new and better estimates. This introduces some problems because if our previous estimates are incorrect, then we're building off of incorrect estimates. So in online deep reinforcement learning, typically what we have is this environment with our agent interacts. So the environment will provide some states and rewards to the agent, and the agent includes typically some deep network where it's using this bootstrapping mechanism that I mentioned in this kind of sort of self-supervised manner. And by doing this learning process, it's able to come up with a policy, which is basically how to act in the environment. And so this policy will give an action to the environment, and we continue in this kind of closed loop. So I'm going to skip the simple example, but basically, there's more than just the deep nets and reinforcement learning. If we have an agent that's trying to navigate this world, it might see fire all around it and decide to never move. And so it might just stay there and not accumulate any reward. But if it were to be a little bit more risky, it might see that if it gets burnt a little bit, it'll find a fire extinguisher and all its streams will come true. So this has nothing to do with the deep nets. It's really just a separate part of reinforcement learning, but just to highlight how complex the problem is. Okay, so I won't go through that. So we have a lot of theory. I have 30 seconds. We have a lot of theory in reinforcement learning, but it's typically limited to linear function approximators. So what we want to do is basically when we publish papers with deep nets, we go through all this theory for linear systems, and then we apply like a DQN, which is a nonlinear function approximator, and get good results with pretty graphs. So what I'm interested in exploring is this space here, which is the deep net that we're using. And there are a lot of assumptions we make about these deep nets, and we don't question these often. And so this is some of the work that I've been doing with Johan and with some other people. So that's what I'll be exploring in the next few years. If interested, let me know. And I will stop sharing now. And we'll move on to our next presenter. So the next person would be Jose Gallego Posada. Sorry. Is Jose here?
Hi, thanks for having me. Today I'd like to talk to you about how multi-objective optimization can help in tackling learning problems with imbalanced data. My name is Jose Gallego Posada. I'm a PhD student at Milan, the University of Montreal, and this is joint work with Juan Camilo Ramirez from Universidad AFIT in Medellin, Colombia. In a recent blog post, Jonas Grave and Ira Korshinova discussed the difficulties that arise when combining in an additive manner several conflicting goals into a single scalar objective. This is a very common practice in the machine learning community, and examples go all the way from empirical risk minimization, where we're trying to balance the performance over different classes, all the way to generative models such as the beta VAE and the use of entropy regularization in reinforcement learning. This additive regularization idea dates back to the literature in structural risk minimization, where we're trying to balance the model's complexity against its performance at fitting the training data. But there are two main challenges in using regularizers in modern machine learning. First, in many cases, rather than deriving the regularization scheme in a principal manner, it's usually justified heuristically. And sort of with the intuition of encouraging certain behaviors in the model, such as sparsity or fairness or exploration or even disentanglement. And moreover, the regularizer changes the properties of the Lawrence landscape. In some situations, this is a good thing because it can turn a convex problem to a strongly convex problem. But in many cases, this influence is not studied or properly understood. And the second challenge is that even when the additive combination of the different functions is theoretically justified, the properties of the data might lead the optimization towards a model that has undesirable behavior. So the sort of standard example of where this can be a problem is in trying to do classification with imbalanced data. So here we have a data set of majoritarily red points, and sort of a standard approach to deal with this is to apply some sort of optimization algorithm onto the empirical risk and try to minimize it. But this is a slippery slope because depending on the choice of loss, you can end up with a model that just decides to, if your loss is, for example, the accuracy, the model can just decide to predict that everything is red and forget about all the examples of all the blue examples. But in applied settings, there might be priorities among the different classes or the constraints to be satisfied when the classifier is deployed. So for example, if you're trying to design a vaccine, then what we want to do is try to get the best performance we can over the whole population, but sort of guarantee a certain behavior on individual subpopulations, as well as having perhaps certain fairness constraints trying to ensure that the performance over different classes is not too different. This has the two advantages. The first one, we have the sort of the hyperparameters are more interpretable because now they correspond to like level sets of these different objectives. And it opens the door for the use of the rich literature and algorithms and constraint optimization and smooth games via this Lagrangian formulation. So we have some preliminary results for the use of these methods for this imbalance classification problem. And here you can see on the right, the result for the ERM method. You see that the performance for the class 1 is very similar for all the methods, but the ERM model essentially just disregards all the blue classes you can see in the predictions. While for the other case, we have two constraints that are forcing the model to perform at a certain level in each of the classes. And via the
Jose,
introduction.
Are you able to finish off?
Yeah, I'm done now. So via the introduction of these constraints, we can easily handle this directly. So we're interested in scaling this to real applications in fairness, generative models, and reinforcement learning. Thanks a lot.
Awesome. Thank you, Jose. Okay, great. So up next, and just a reminder, there was a question in the chat, just in case people didn't see. The question was, how do we connect with a researcher that has pitched their project? Can we volunteer to collaborate as students in one of their pitch projects? And yes, the idea is there will be a follow-up form to this event. So do take note of the pitches you're interested in and the presenters, as there will be a follow-up form where you can express interest, and then we'll try to make those connections happen. Okay, so up next, we have Benjamin Sanchez-Lengling from Google Brain.
Yeah, how's it going, everybody? It's awesome that you're organizing this workshop, and you know, that we're having this, like, you know, buffet of ideas. So I want to pitch one, and this is based on some results that we recently found. I work on graph neural networks. I work on SMEL, and one of the things I care about is learning, understanding explanations of mechanistic explanations of why things do the things they are for graphs. And in particular, we have this work that came out in Europe 2020, where we start to like evaluate different types of attribution methods, different ways of building explanations on graphs. And sort of what we can do is we can, you know, you might have already heard of graph neural networks. You can think about it as a neural network that takes a graph as input and it outputs a graph. And there's like special stuff about it to make it work for graphs. And what we can do is we can set up a synthetic task where we know the actual reason why something should give you a certain label, and we can set up a task to see, like, oh, is this attribution method better or worse? In which axes is it worse or is it better? Or how can we trust it? And this is important because we want to really build credibility for our models. And one of the curious things we found is that, you know, we can set up this task. In this case, we're trying to predict 3 different types of subgraphs inside of a graph. And turns out that for randomly initialized neural networks, for graph neural networks, you're going to already have, you can find already really good networks already, like, by randomly. And how do you find that? And you probably have heard before in other papers, graph neural networks have a strong relational inductive bias. Another way of saying that is graphs are good at learning graph structures. So are there ways that we could initialize our networks that take into account the graph structures we're expecting? And so, you know, this is the last one. It's like a request for plot. If I was imagining working with somebody, if we were like collaborating, this would be probably the first plot we would want to make. Kind of what we would maybe hope to find is that attribution priors give better initialization for graph neural networks. You're probably not going to get better models. But if you train 50 models at random, what you're hoping is that you're going to get better models overall. So you're going to get a better distribution. And this is always better because if we can initialize a neural network and get really good performance from the start, you know, there's less randomness in it. And there's a lot of questions attached, right? Why not? What can we fine tune and find a strategy that gives you this prior for each problem? And yeah, that's it. And yeah, email all that stuff there, and you know, I think there's a form at the end.
Perfect, right on time. Awesome. So there was an idea to let people know a bit more in advance when they're presenting. So I don't know if Isabel is ready.
Sure. So I can definitely present on that part. So let me just put my slide in presentation. So here I'm talking about identifying adverse drug events and relationships in clinical text and multitask learning. So for me, I actually have a clinical background before switching to working in machine learning and artificial intelligence. And for me, it's because in that one time in the hospital, we had a patient who died And unfortunately, we had provided the wrong medication. And ultimately, that issue was, we should have been able to have corrected that, but it was in the text, in that history and present illness note. Nowhere else in the EHR system would have probably detected that. So here, I guess I know I'm kind of behind on time, but essentially I worked to do a prototype project with Kung-Yun Cho, one of my mentors at NYU, and another mentor at the medical school, to build a multitask learning system that would also detect both entities such as drugs, adverse reactions, as well as their relationships, so how they're related together. So this is really the background for it. So, adverse reactions, they really, almost half of all drug-associated deaths are due to errors. So I can go a little bit into that system. So it is a multitask learning system. We use a bilanguage model and a convolutional neural network to detect relationships. So it's at the same time, and we used a ranking loss function. So I can definitely go into details for that, but I know I'm kind of running late on time with this one. Sorry. So that's all I have for this one. Sure. So for this one, this is a clinical natural language processing interface over electronic health records. So English question to SQL query. So the motivation of this work. So I had already built a prototype interface on the Mimic database. This is a publicly available database of electronic medical records. And the importance for this is really to think about how we can provide help to clinicians. So imagine if they want to ask a question like, what patients, how many patients died from once we gave them this drug after another scenario. So essentially I crowdsourced questions. So I talked to other clinicians and pharmacists, and I said, oh, what kind of questions might you be interested in? And constructed templates. So here, this is the template. How many patients with problem 1 were given treatment? So diabetes and insulin. And then I manually extended it, and I had a assistant help with the SQL query, writing the SQL queries to match the questions. And then we utilized paraphrasing techniques to extend the data set. So here you can see we're using named entity recognition as well as sequence to sequence. In order to kind of extend those questions, we use the paraphrasing database. So as you can see, one question might turn into 3. And then here below, you can see the SQL query for the database. Essentially, this is the overall pipeline. So named entity recognition, sequence to sequence with attention, and then actually connecting to the database and evaluating. So this is kind of just the first NER iteration of this. So it was just trained on a clinical NER database. It has 6 entity types, so problems, tests, treatments. And then the sequence to sequence with attention, this was used for the translation part. So using, and a little bit of background about our data set. Right now, we've made it larger, but what I'm showing here is that first iteration where we only had 450 question pairs. And actually, this is comparatively similar to the results on the Geo and Jobs SQL, English question to SQL, which is typically kind of a smaller data set. So we evaluated the prototype in 2 different ways. So, if the SQL was if the NER was correct to the golden standard, but also if the sequel was created. So this kind of just explains some of the results that were done, and kind of the next steps would be building upon that, really thinking, most of the question and SQL pairs that we have are things with fixed cardinality. They're simple SQL queries. So what was the main admission reason for patients who were given, a certain drug intramuscularly, and we really want to think about how do we actually create questions such as, what patients had a 30% increase in serum creatinine and no dose adjustment, things of that sort. So again, thank you. That's all I have.
Great. Thank you, Isabel. So up next, we have Roseanne Liu from Google Brain.
Okay. Hi, everyone. Thanks for having me here. So I'm presenting a simple idea. This is actually an original idea from Zubin Garamani, and we hacked on an early version of it, but this is a very much simplified idea from that work. So I call it safe regions for neurons. So basically, you guys should all know this. This is ReLU, one of the most important ideas, arguably, that made deep neural networks work. But it's kind of scary that it has this linear region that keeps going. That means that, however, if your input gets really large, your output gets really, really large. There's no saturation. In Zubin's word, biological neurons don't do that. So it's kind of scary to us. If you can think of what happens on the ReLU level, so basically every input at the point of ReLU for each neuron is condensed into one point along the ReLU line, of course. So some of them get smashed into 0, and some of them are on this linear region. So first question I want to ask is, how are the dots distributed? For example, in this case, maybe all the dots are sort of like condensed here, but it's sort of like a asymmetrical distribution, something like that. And assuming we're having a very simple distribution, we don't care about the shape of the distribution, but we just care about the range. So what is the range during training? During training, you see many dots here, and assuming during task you see different dots, and maybe it was out of the range, in the range. What's the relationship there? Can we talk about generalization from just seeing the range shift? And let's say the range seen during training is the safe region, because it's the range that the neuron is comfortable with because it has seen it during training. Now we can extend the range slightly, even over the max and min, just for generalizability, just kind of relaxing the constraint. Now for each test example, a neuron can really tell if it's in region or out of region and how much, because each test example is also a dot along this line. So if you agree with that premise, basically every neuron has this value, and every neuron would have a safe region. Some might shape something like this as the example before, but some are probably a little odd. Maybe during training, all it's seen is 0, like this neuron never fired. Some are having all kinds of weird shapes. And now if you have an input, which is say is a cat, you can imagine it just landing on different regions of each neuron of this neural network, right? And now each neural network would have a label that would say, oh, this dot is in region. It's in the region that I'm comfortable in. This one is in, this one's out. I've never seen any dots during training that's so far away from the safe region, something like that. So basically for each neuron, you now have a signal that says if it's in region or out of region. Now, what can we do with that signal? We could collect this data and use it to understand many things. For example, maybe out of distribution detection can be understood by just seeing lots of out of region signals or not. Who knows?
Roseanne, do you mind are you almost done?
Yeah, this is the last one.
Okay, perfect. Sorry.
Okay. And maybe adversarial task also can be seen by lots of out or lots of in, who knows? And pruning maybe can explain by this. And the final question is, can we observe any patterns? Cool, I'm done.
Perfect. Thanks so much, Roseanne. Okay, so up next we have Dagoberto Pulido Arias.
Okay, so I'm going to talk to you about this new research problem that I am starting to work with. So this is about semantic detection of changes in satellite images. So basically we want to develop a methodology that help us to quickly generate information on the effects of the pandemic on anthropogenic phenomena, such as the economy. So our approach for solving this problem is to use satellite images, more specifically Sentinel and synthetic aperture radar images. So this kind of images come from an active sensor that sends a pulse to the ground, and then the pulse is returned to the satellite, and then it generates an image. So this is the kind, well, the first thing that we are doing for solving this problem is taking samples. So we're choosing random points in Mexico City. So we are obtaining the SAR Sentinel images for those points. So up next, we want to be able to generate change maps. I mean, we want to use some kind of, maybe some kind of neural network to be able to detect changes between those radar images. So then we can correlate or find relationships between the changes in those images and anthropogenic phenomena like the economy, or how vulnerable people is being affected by phenomena like the pandemic, for example, where many people have to stop their activities. For example, what we are looking here at the screen is a change map using a classic method. This was not done with a neural network, but we want to find a better way to solve this problem. This is a method based in statistical methods like from the 90s, and I think neural networks could maybe something that use attention, or maybe some kind of recurrent neural network could be useful to solve this problem. So in this way, we want to be able to know how different people is being affected by the thing that happens, but we want to be able to observe that in a big scale, like in a city-wide scale, or maybe country-wide scale. Thank you.
Thank you very much, Dagoberto, for staying within the 3 minutes. So I don't know if Lucia is here.
Hello. Yes.
Okay, perfect.
Can you hear me?
Yes, we can hear you.
Okay.
Are you able to share your screen?
Are you able to see the presentation?
Right now, it's just a black screen for me.
Yes.
Oh, there we go. There we go.
Yeah. I think it's a little bit of patience with the computer. Thank you for this opportunity. We'll start now. Machine learning for art reconstruction. This is a project we are presenting for mentoring. This is a project of machine learning for art reconstruction, and we are using a use case of a particular lithography from Escher as an application of our idea. This is the lithography that Escher made in 1956, and as you can see, it has the center blank. That means we are trying to create a methodology to complete the center. This problem has been open for 65 years. There has been some attempts to reconstruct what should be in the middle. I don't have time now to show why we think we can do better. Particularly, we're trying to use machine learning to complete the center, some machine learning techniques. We think this will be beneficial as a beneficial research, because we will be pushing the boundaries of what is called in-painting, so deep learning in-painting or image synthesis. And also, I think this is a project that will attract a lot of interest from scientific outreach, because Escher is a well-known painter. This is a painting that has been around as a mystery for years, and we are just adding a flavor of machine learning. So what's not to like in this project? This is actually very challenging. We know that computer vision works very well, and machine synthesis works very well in the machine learning umbrella. This painting in particularly, we say that we're pushing the boundaries because it's actually very challenging, because it has a mathematical structure that we need to respect. This is the mathematical structure behind the painting. As you can see, we put a grid to show you how the painting spirals inwards. As you can see, the painting is spiraling inward. And we were, with this spiraling, we took the parameters of the spiral. There's literature on this. I'm not gonna go because otherwise 3 minutes wouldn't be enough. But believe me, we have unveiled the mathematical structure. Following the pattern, we were able to complete part of the center. As you can see, there is a self-repeating pattern that goes in the middle. Don't ask me why. We can chat in other time how we came to this conclusion. Just we were able to fill half of the center just with mathematics. Now, our task is to complete the rest of the center. You will see here that is a blank area between the self-repetition of the painting that you don't understand why the painting is self-repeating. I can explain later, but there is a self-repeating pattern. We were able to fill half of the white round circle with it. We just need to fill whatever it's in between a square and a circle. I mean, you obviously cannot fill a circle with a square, especially because the pattern tells us that the square in the middle is really, really small. And now the last one is, this is our attempts to complete what is missing between the square and the circle. As we have used Common GANs, and we are now applying attention models, some success, some unsuccess. As you can see, the spiraling effect is partially captured. And this is obviously not right yet. So we are looking for mentoring for someone who is more familiar in painting, attention transformer models, image GPT, whatever we can get in more expertise. This is a team of 4 that we're working, different levels of seniority, but I believe some mentoring on in painting will be good. And this is some bibliography that you can read more on the painting, but everything that has been done before doesn't use machine learning. So we believe that machine learning can solve both the problem of the spiraling effect plus completing what is missing in the center region. Thank you.
Thank you very much. Really fascinating. I'm a huge fan of MC Escher.
Thank you.
So up next, we have Sarah Hooker from Google Brain. I think she's just joining. I don't know if Sarah's already there. Okay, so until she joins, I think she's just trying to join the Zoom right now. A couple of questions that came up. So there's a question about having a Discord or Slack or something like that where we can continue discussing. As I put in the chat, there is the LXAI.app where members can join, and anybody can join really, and you can start a discussion there and have these types of research collaborations. But in addition, as I mentioned previously, there will be the follow-up form where you can express interest directly in one of the projects, and then we'll try to make those connections happen. Okay, so I see Sarah is there already.
Excellent. So lovely to be here. I wanted to share a little bit about maybe both my research interests and what might be fun to think about. So I'm a research scientist at Brain, and my research agenda to date has focused on training models beyond just test set accuracy. So this is training models to be compact, to be robust, fair, to fulfill multiple criteria at once. And I recently did very interesting work with my collaborator, who is Chirag Agarwal, and actually also Daniel De Souza has been involved in an updated version of this work that is currently under submission. And this work is really trying to understand what examples does a model find challenging during training. And it's clustering according to score. And this was framed really as an interpretability tool to allow different practitioners to surface what they need to look at to audit. However, what I think is an interesting extension of this work, and what could be fun to think about, is once you've computed this score, you really have a signal of what examples are more important for a model. And we know that these aspects emerge early in training. So we know early on what's easy and what's late. So the question that I think is interesting is, can we move away from this current model where we treat all examples uniformly? We do a full forward pass, a full backward pass, and can we move towards something which is more adaptive in nature, and use these early signals to essentially separate examples? I would say at the risk of this project, I would frame it as medium. So there's still some unknowns, but some of it has been de-risked because of the project setting up the scoring. And this would be with Chirag. So Chirag is at Harvard, and he's a co-mentor on this project. So I'm going to pause there. I'll return the time to Pablo and I have 1 minute left, so I will invite questions. So if you put anything in the chat, I'm happy to answer with my 1 minute. Or we can count down the clock.
So if there are any questions for Sarah? So there's one presenter left from who? Oh, sorry.
Okay, so Joan says, would that work for NLP? And David says, which models are you training? So Joan, yes, it would. It's based upon gradient-based signals, so any gradient trained model, but that's also an interesting extension. And David said, which models are you training? So right now, this is all in the computer vision space, but our emphasis is in supervised deep neural networks. Oh, Joan's already going for unsupervised. Interesting. I would have to think about the structure of that. So presumably you can still get some signal from an unsupervised method like contrastive learning. So I'm going to pause there. There was a lot of questions at once, and I know we still have one presenter, but I'm glad to see this has piqued the interest of a few people. So happy to follow up afterwards. Oh, Matthias says related work. Okay, so definitely everyone take a look at that as well.
So yeah, the next presenter is Abhishek from Google Brain. I don't know if he's been able to join yet. So maybe what we can do is start the discussion, and we can continue if you're already answering some questions, Sarah. Feel free to handle the ones there. If other people have questions, are you able to raise hands here? Doesn't seem like it. Okay, so you can either post them on the chat. I think maybe post them on the chat so we don't have too many people talking. And I'll try to ask them. So Sarah, you were in the middle, I think, of answering a couple questions.
Yeah, so Mariella says, you mentioned interpretability. Can you be a bit more specific on that? Yes, that's a good question because it's very broad. So in fact, some of my other work is on local explanation methods and measuring the reliability. So those are methods which essentially try and understand model behavior for a single example. This approach, how VOG is framed, is really understanding relative importance. So you have an entire data set and you're trying to surface a subset of that data set, which is more challenging or easier. And William says, what is the scale of risk for projects? So this is my assessment. I always like to try and, I guess, if it's risk or medium, I try and communicate that because it's also, you know, the time of people involved. So I would call this medium because although there's a scope in place and there's a code base in place, whether this will work for accelerating or changing training in a positive way is an unknown. Also, the data sets will initially be trying a small scale, but are fairly saturated. So like CFAR 100 is a good data set to try out on, but we may not see the improvements before we actually scale to something more meaningful. So these are all reasons I would call it medium, meaning it could be very promising, there's basis in place, but it could not. And then let's see.
So Pablo is asking, can this be related to the forgetting problem? I assume that's referring to catastrophic forgetting.
So it's interesting. Catastrophic forgetting typically occurs more during when you train on one corpus and then you try and translate to a new corpus and you can't return. So there is an interesting aspect around whether there's some difference in what examples you do forget versus which examples you don't. That's actually an interesting underexplored question. Presumably, my hypothesis would be is that the examples you have to memorize, so the harder examples that you memorize later in training are the first to be forgotten. That would be what I would suspect. But I wonder if there's work done on that. Whenever I think of, oh, that's an interesting question, I'm like, has someone already done it? But yeah, excellent question.
And I see we have Abhishek here. So maybe we can, he's the last presenter of this pitch session. And then so what we'll do is we'll have Abhishek present. If anybody has questions for any of the presenters, please put them in the chat. And so we'll be able to stick around a bit more since we started a bit late. And I'll try to moderate the question. So please specify the speaker the question is directed at and what your question is. All right. So Abhishek, are you able to share your screen?
Yeah, so this idea was about debugging what happens when we fit images with autoencoders. So we have seen that GANs are really good at generating good images, and while at the same time VAEs or autoencoders, they sort of struggle to generate sharp images, especially with the lower dimensional latent spaces. For example, VQVA2 and even the recent NVAE, they use a much larger dimensional latent space. So VQVA2, it is about 5,000 dimensional. NVAE is even larger. At the same time, Big GAN or other state-of-the-art GANs like StyleGAN, they use an order of like less dimensional latent space. For example, Big GAN is about around 160. So this raises a few questions that I have listed here. The first one is, could it be due to the issues related to optimization? Especially because we have a low dimensional bottleneck in the autoencoders. Does it present any challenges and shapes the landscape in a bad way for optimization to work well? The second question that arises is, could it be due to the fact that the maximum likelihood objective asks us to cover all the modes of the data, and this stresses the autoencoder or VAE to be able to not cover everything well, and we get sort of blurriness in the images. So we can do some experiments to kind of tease apart these two issues. First experiment could be that we take a pre-trained GAN with the same decoder architecture as the autoencoder, and take images sampled from this the generator of this GAN, and train autoencoder on these images. The first version of the experiment could be we take these latent encodings and image pairs from the generator, so ZX pair from the generator of the GAN, and use it to train a decoder only, and we can keep the architecture to be the same. So we know this should succeed because there already exists a decoding mapping that's there in the GAN that can generate these images from the Z's. I think the things to be seen here would be that how does the optimization work, especially in the case when we are going from low dimensions to high dimensions? Are there any challenges there? The second version of the experiment, which is more difficult, would be to train both encoder and decoder on these sampled images from the GAN. So here, I think this experiment will take out the mode coverage issue, and we can rest assured that the problem, if we see in training, would not be due to the fact that it needs to cover all the modes, because we know that a GAN has already been trained on these. A GAN can generate these images, so the modes can be covered with a decoder of the same architecture. And we can look at the plot of reconstruction error versus as we vary the number of samples we get from the GAN for training. The second experiment we can do could be to fit an autoencoder on a small number of real images. And we can see how the reconstruction error varies. The average training reconstruction error changes as we change n. How does it fit small number of images? I actually did some experiments on the second front where I was fitting like 10 images or 50 images using ResNet autoencoder. And I was not able to get like zero reconstruction error with ResNet on 10 images. So this also
Abhishek,
could be an interesting.
if you don't mind wrapping up.
Yeah, just one more slide. We have some next steps that can be done here. If we find out if it's an optimization issue, we can look into the second order approximate methods that have been recently proposed for better optimization of autoencoders. We can also look at some architectural changes, maybe having some skip connections that people have already explored, but slowly annealing the strength of the connections via regularizers, so that at the end we have a clean, without skip connections autoencoder. But we can see whether it shapes the landscape in a meaningful way as we anneal these skip connections, and does it help the optimization? And on the other hand, if it is found out to be a mode coverage issue, then we have to, I guess, need to think about ways to trade off sample quality with mode coverage. Yeah, if any of you is interested in the topic, please feel free to reach out on this email. Thanks a lot.
Awesome, thank you, Abhishek. So it's 11 for me, 8 for you, but we're able to stay a bit longer if people are able to.
Yes.
So yeah, so there were a couple questions. There was a question to Roseanne, but I guess she already answered. So feel free to, I think we can maybe make this a bit more ad hoc and just start if you want to open your mics to ask questions. One thing I found really interesting is that there seemed to be kind of almost like two tracks to these pitches. There were some that were kind of using deep learning methods for an applied problem, whether it's like filling in MC Escher drawings, or using it to uncover relationships in satellite imagery. But then there's another side also in trying to uncover some of the mysteries of deep learning and why it behaves how it works, and why does it work so well, and do we need all of that? And I wonder what people's thoughts are on this kind of parallel track. Is this sort of how you see the research community going forward, or is there something that was missing from these pitches, that an area that you would have liked to see?